So we're talking about decimation and interpolation. Okay, welcome back to part 2. So just to recap what we were doing before the break. So we're talking about decimation and interpolation, in particular decimation in this case we want to reduce the sample rate. And so what we said was that in order to reduce the sample rate, we're going to need to use a decimation filter first. And so this is the process that we use when we're using our decimation filter. And so it's a process of filtering followed by decimation. And so we'll write this in a diagram of a filter first, so low pass filter, followed by some decimation or downsampling. And typically in this case we'd write this as downsample by 4, so a down arrow followed by a figure. So this is our decimation. So if we want to indicate what the sample rate is in this, we'd use a line through it. Sometimes you use the line through it to indicate the number of lines that you've got. Here we'll use it to indicate the sample rate. So here it might be 192 kilohertz. We've gone through our low pass filter, we're still at 192 kilohertz. And then we decimate or downsample by 4, and we're now at 48 kilohertz. So this is the 2 stages that we need. If you ask MATLAB to downsample or decimate for you, it will actually do both of these in one step. So MATLAB will include a decimation function. It will do a low-pass filter first, and it will work out what low-pass filter you need in order to do the decimation. But what's this decimation step here? So here, this decimation box, this one with the downsample by 4, what this actually does, you just remove 3 out of every 4 samples. Or in other words, you keep 1 of 4 samples. So here's an example of what we might do. We might have a signal here that's represented by a number of samples. And we would just keep 1, skip 1, 2, 3, keep the 4th one, skip 1, 2, 3, keep this one, skip 1, 2, 3, and if that carried on down here, we keep that one. So let's go back up here again. Yeah. So we've here got all these samples. This one, we drop this sample, that one, and we take the next one. We drop that one, that one, that one, keep this one. Drop that one, that one, that one, and keep that one. So actually the process of downsampling is quite simple in the sense of we just do the obvious thing of throwing away all but 1 out of every 4 or 1 out of every n samples if you want that. But the thing that's allowed this to work is that we've done the low-pass filtering first to make sure that this is, if you like, sufficiently smooth so that this lower number of samples can represent all the information that we want. So now when we're actually wanting to do calculations with this, we need to know how expensive is this. So how expensive in terms of how many multipliers?
Double the size of the input will double the size of the output. That if we multiply the input by A, we multiply the
Because it
output by
actually
X,
turns out to be
that's linearity.
cheaper to do this filtering than we might at first
But
think,
I've just picked up a couple of things that
either for downsampling, decimation that we're doing here, or for upsampling, which we'll see next. So let's just look at how much a regular filter would normally cost to do. So here's our regular filter that we might have. So cost of filtering. So we've got some sort of signal coming in over samples n, values x of n, and here are our samples coming through. And if we build a filter to filter that, our x of n is coming through. Let's assume that we're going to make it as a finite impulse response filter, FIR filter, but we could just as easily make it out of other filters. Our x comes in here, and we have z to the minus 1 box chain down here. What's the z to the minus 1 stand for? Yeah, 1 unit delay. So z to the minus 1, 1 unit delays going down through here. Okay, z to the minus 1. And we're going to multiply by various parameters, A0, A1, A2, all the way up to a big N for an nth order filter. And then we're going to add them all together. And this is going to give us our yn. So this is a regular filter order n. So every sample needs how many multiplies? So we've got n items down here. We need to multiply by each one of these things and add them up. So how many multiplies do we need per sample? Big N. Yeah, every sample needs big N multiplies. So e.g. at 192 kilohertz for a 10th order filter, the number of multiplies per second is the sample rate, fs, in samples per second times n, so fs, which is samples per second, and n, which is multiplies per, oh sorry, we're off the bottom. Yeah. And n, which is multiplies per sample. So that is, in this case, 192 times 10 to the 3, because sampling frequency is 192 kilohertz, which is 192 times 10 to the 3 hertz, times n, which is 10. So that's 100, well, let's write it as 1.92 times 10 to the 6 multiplies per second. So 1.92 million multiplied per second are the number of multiplies we're going to need to do the filtering at that rate. But we might not need to do all of them if we're going to downsample it afterwards. So let's have a look at what happens. That's our default filter. But if the filter is followed by decimation, spell that correctly, decimation, or downsampling, by 4, we only need 1/4 of the sampled outputs. We discard 3 out of 4 outputs. So don't calculate them. So let's not calculate all of the outputs from our filter if we're going to throw most of them away. We only calculate the ones that we're going to need. So let's look at this from a diagram perspective. So here's our regular filter, x of n, with our samples here that we're going to want to filter. And suppose we've got, let's say, an order 4 filter, calculates from those, gives an output. Actually, I'll put it at this end so we've got a bit of space. Y of 0 from those 4. We've got shifted version here, calculates a Y of 1 from those 4. Got a shifted version, calculates Y of 2 from those 4, and so on. But actually, we don't need most of those. Here's our filter again, our signal. That's our n. We need our Y of 0. We don't need 1, 2, or 3. The next one we want is Y of 4. And the next one we need is Y of 8. So what that means is, instead of having to calculate the filter at the length of the filter times the sampling rate, we only need that divided by the decimation. In other words, so we need n times fs over 4 multiplies per second for decimation by 4. Or in general, for decimation by d, we need n times fs over d multiplies per second. So for this example, 192 kilohertz decimated by 4 using n equals 10th order filter. We need 192 times 10 to the 3 over 4 times 10. So 192 over 4 is 48 times 10 to the 4. That's 480 times 10 to the 3. Multiplies per second. So we actually only need to calculate this filter at the lower sample rate. So calculate the filter cost at the lower sample rate. So that means it's cheaper to build this decimation filter than we thought it was to start with. We just have to make sure that we don't even bother to calculate the things that we're going to throw away afterwards, because there's no point in calculating something if you're not going to use it. So this helps. So this means there's less calculation than we have to do when we're doing downsampling or decimation. And there's a similar thing that we're going to find when we do upsampling or interpolation. So let's look at that next. Is this okay so far on here, though? Okay, good. So let's now go on to the process of upsampling. So upsampling or interpolation. Now this time, to do upsampling, we start at some input. Instead of doing the filter first, we have to do the upsampling first, followed by the filter. And I'll talk about the filter design in a moment. Low pass filter, and then out comes our output y, say y of m. So, for example, here we might have 12 kilohertz FS1, sample rate 1. We interpolate or upsample to get 36 kilohertz. If, suppose, e.g., we use I equals 3, then the upsampled version, FS2, is at 36 kilohertz, and then our low-pass filters that at 36 kilohertz. So how do we do interpolation? So conceptually, you can think, well, if we've got a small number of samples here, let's say we've got our x of n that's coming in as a signal that looks like this. This is our x of n coming in over n. Suppose we wanted to put some extra samples in between these that were so-called interpolated. We might think, well, we could draw a straight line between these and do a linear interpolation between those samples. That might be one thing we could do. We could use some sort of cubic spline curve or something to join them up. We could interpolate them in that way. But we're going to think about this from a process of signal processing. Rather than thinking what we do in the time domain, we're going to think about what we do in the frequency domain and then work out what the time domain is going to tell us in order to join these up. So let's have a look in the frequency domain. So this is in the time domain over here. The frequency domain is over here. So here's our frequencies. We're going to leave plenty of space. Here we've got, we want space to go up to sample rate of 36 kilohertz. So we want space for, that's going to be 24, that's going to be 12, minus 12, minus 24, minus 36. So currently, this is our FS1 minus FS1. So our Nyquist limit is currently here. So this is where our frequency representation is. Looks like this. These are supposed to be copies of each other. Repeated every 12 kilohertz in the frequency domain. Okay? So this is just 12 kilohertz signal, and this is what its frequency representation is with its baseband copied every 12 kilohertz. Now, suppose that we were going to not change this signal here, but just change the sample rate by putting extra zeros in between here. So let's call this x dashed of m. It's going to have the same samples as the original signal, but we're going to have some zeros in between. So these extra zeros between the samples brings the sampling frequency up. So we're now at fs, instead of fs1 equals 12 kilohertz, we're now at fs2 equals 36 kilohertz. But because we haven't actually changed, in essence, what the signal is, the repeat pattern is still the same. So at 0 here, we're at fs2 36 kilohertz, and there's a sort of Nyquist limit, in theory, in between here, but this frequency shape is really still the same. So we've still got this repeating pattern here. So now these things in here are now, this is now aliasing inside the upsampled signal. And in order to get rid of this aliasing, we now need to use an interpolation filter in order to get rid of those. So we now need an interpolation filter, which is going to keep the real signal down here, but get rid of the aliasing section up there. So keep that. So this is our 0, this is our fs2 minus fs2. And so the result will be what was originally a low frequency signal no longer aliased inside this higher frequency signal here. So now the aliasing is removed, and we're just left with the baseband. So we've now done our upsampling. It hasn't improved the frequency content in here, because actually there was nothing else in there to start with. This is the best that you can get. But what you have got is a smoother version of the signal. So now what we've got is our original sampled signals here, but we've got points in between them that have now been filled in at the higher sample rate. So this is now our output y of m. So you can see now that it has done interpolation, but it's done it using a signal processing method. Suppose this were an ideal filter or a nearly ideal filter, what would it look like? What are ideal filters that have a sort of boxcar shape look like in frequency domain? What sort of time domain representation would a boxcar filter have? A sinc function. Yeah. So this is actually the filter that you've got is actually a sinc function. So this is the type of interpolation filter that you've got. And actually it goes through 0 and every other sample that was in the original signal. So what that means is that every sample that was in the original one is kept exactly the same in the output, but the points in between are filtered by this sinc function. Linear interpolation, by contrast, would actually look like a ramp or a sort of triangle. And so actually if you took that bit and approximated by a triangle from there up to there down to here, this one would be a sinc, this one would be linear interpolation. So linear interpolation is actually an approximation to an ideal filter. It's a pretty crude one, but it'll do a decent first job. That's why linear approximation looks reasonable, but it does not really get rid of all the aliasing over here. Yeah. Oh yes. So if we look at the distance from this sample to that one gives us into the 1 point in the middle of a sinc. So sinc has a 1 at the top, and then every time we get to a 0 here, that exactly lines up with that 0. That exactly lines up with that 0. That one exactly lines up with that 0. So that means that the sinc curve completely ignores any of the things outside when it decides on calculating the sample in the middle. You get exactly out what the original sample was. So it doesn't change any of your original samples. But what it does do when you're shifted off to one of the intermediate samples, it will take all of the samples into account when doing that, or most of them. Yeah, question. The required bandwidth of the low-pass filter, this one has got to be the, so this was our original FS1 over 2, that's its band limit, FS1 over 2, minus FS1 over 2. So in this case, this was 12 kilohertz, this would be e.g. 6 kilohertz for that one. So you have to low pass to the Nyquist limit of the original signal after you've done the upsampling. It's because you're using it as a filter, so you convolve this filter with the input. So you take your input x dashed of m, the one with the zeros in it. This is sometimes called zero stuffing, to put the extra zeros in. And then you convolve with a filter made up like a sinc function. It has to be truncated for reality, and then you'll window it as well, in just the same way as that we would have created an FIR filter. But that FIR filter just helps to smooth out the rest of that, smooth the signal so that the points in between end up smoothly interpolating in between the ones you had before. So once you've in fact, I think one of the past exam papers had a question about how good linear interpolation is. You can also think about square box interpolation, or sort of sample and hold interpolation, what that does. And so that approximated that by, instead of a ramp on either side, just by holding onto the same number of samples. It's a very crude interpolation, just say, keep the same value each time. So that, again, it's a convolved one, so it will be, essentially ends up being repeated each sample in order to do the interpolation between the previous samples. But this time it's only looking at relatively local information. So here's our thing. We've got our upsampling or interpolation here. And then here we've got the interpolation filter, which is a low-pass filter created from a sinc function or something approximating a sinc function. So that's how we do it, but now again we've got the question of how costly this is going to be in terms of the number of calculations to do this. So now, how expensive, and this leads to the idea of the polyphase filter. And we'll see what this means in a moment. So let's just leave the last couple of bits on there as we go on to this. So we'll want to build this low-pass filter as some sort of Ym is based on the samples of x dashed m here. So Ym is, let's say, h0 of x dashed m plus h1 of x dashed m minus 1 plus h2 of x dashed m minus 3 all the way up to dot 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 let's say h8. We're going to do this for a specific example of m minus 8 for 0 up to 8. So this is a 9-tap filter, or order 9 filter. So we've got 0, 1, 2, 3, up to 8, so that's 9 multiplies that we've got. So this looks like it's 9 multiplies per sample. But let's look again at what x dash m looks like. So x dash m is something that it has a sample at m equals 0, then it's got 2 zeros. It has another sample at m equals 3, then another 2 zeros, then another sample at m equals 6, another 2 samples, another sample at n equals 9, and so on. So let's see what we get if we calculate, let's say, y of 9. That's, well, let's go through all of this. h0 x dashed of m is 9, plus h1 x dashed of m minus 1, which is 8, plus h2 x dashed of m minus 3, which is 7, plus h3 x dashed of m minus 4, which is 6, and so on. But x dashed of 8 is 0. X dashed of 7 is 0. Many others are 0. By the time we get to x dashed of 8, x dashed of 1, 9 minus 8 is 1, x dashed of 1 is 0. So actually all we end up with is h0 0 x dashed of 9 plus h3 x dashed of 6 plus h6 x dashed of 3. We don't need to calculate the ones in between. And because from our previous slide, this one came from the very first sample of this one, so this x dashed of m here is actually equal to the original x of 3, because we've calculated 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We've only gone 0, 1, 2, 3. So that one's x of 2, that one's x of 1. So it's actually equal to x naught x of 3 plus h3 x of 2 plus h6 x of 1. So this now looks like 3 multiplies per sample instead of 9. And in fact, if we do this for other values, there are 3 slightly different versions of this filter depending on which phase the subsamples happen in. So for when m is an exact multiple of the 3n ones here, we get y of m is equal to h naught x of n plus h3 x of n minus 1 plus h6 x of n minus 2. So that was the example that we had here. When m is 3n plus 1, we get the mth output y of m is h1 x of n plus h4 x of n minus 1 plus h7 x of n minus 2. You'll probably see the pattern here, where m is equal to 3n plus 2, y of m is equal to h2 x of n plus h5 x of n minus 1 plus h8 x of n minus 2. So that means that in order to get the single output at 3 multipliers per sample, we actually need to create 3 slightly different filters and merge the output of those 3 filters. But the advantage of doing this is that each of those filters only costs us 3 multipliers per sample instead of 9 multipliers per sample, which we'd have to do otherwise. So we can summarize that in, if I just keep those 3 equations there for the moment, we can summarize that on a whole flow diagram. X of n coming in, this is our original low frequency at fs1. We've got 2 delays, z to the minus 1 and z to the minus 1 boxes here. And then we've got 3 different types of filters. So one filter takes I'll put arrows along the side here like I used for the FFT to represent multiplication by H0, H3 and H6. And that gives us our output for when m equals 3n. Then we have another filter here that we add up the values for this one, and this one multiplied by, this time, H1, H4 and H7. That gives us the output when m equals 3n plus 1. And then the next filter, take those same three outputs, and multiply this time by H2, H5, and H8. That gives us the output for M equals 3n plus 2. And then we use a rotating output as a selector to give us our y of m output here. So this, this set here, is at the low sample rate. And the output here is at the high sample rate. So this is just the diagrammatic way of writing these equations at this point. So now our computational cost is now L taps of the filter times the low sample rate. So e.g. for upsampling 12 kilohertz to 36 kilohertz with a 9-tap filter, we have 9 times 12 times 10 to the 3 equals 108 times 10 to the 3 multiplies per second. And this is the polyphase filter. So the reason it's called a polyphase filter is that you've got essentially 3 subfilters in here, or a number of subfilters, where each one operates at a slightly different phase of the signal. So really what this means is that for either upsampling or downsampling, the filter operates at the low frequency rate of multiplies. So if you want to work out how expensive a filter is going to be, you always use the low frequency rate, because either you can use the polyphase filter if you're doing upsampling, or you can do skipping calculations if you're doing downsampling. Okay, so that's really it for this lecture. The tutorial 9, questions 1 to question 4 are covered by the material so far. Next week we'll be doing multi-stage, multi-rate, and Z transforms. So how do you take a Z transform of changing the frequency sampling rate? That's a bit of an interesting one. And also the revision material is already out, so you might want to start preparing for that, and then we'll cover that in our final week. Okay, thanks very much. I'll stop for now and see everyone next Monday.